Oh, I can. Can anyone hear me?
Not yet.
Oh,
I
hello.
mean, yes, still. Okay. Okay, so let me first introduce you. So, welcome, people of the pre-seminar. Our speaker is Austin Scheiner from Oxford, and he's going to tell us about existential embeddings of R and Z. Please.
Thank you very much for letting me speak here. Today, I want to talk about existential embeddings of the hyperfinite 2-1 factor R and the Jiangsu algebra Z. On the very first slide, however, I noticed I have one small mistake, which is this is 2025, not 2024. Hopefully, this will be the last typo on the slides. Yeah, cool. So the outline of the talk will be as follows. First, we're going to introduce the hyperfinite 2-1 factor, which we denote R. We're then going to talk about why R is so special and all of its special properties. We're then going to introduce the Jiangsu algebra Z, which is going to be some C-star algebraic analog of R. We are then going to introduce a very important construction in the world of C-star algebras and Neumann algebras, which are ultrapowers. And lastly, we'll talk about one connection to model theory and one question there, which has uh, which has to do with existential embeddings of R and Z. Cool. So, how do we construct R? First of all, let's start with just the two by two complex matrices, right? How can we send the two by two complex matrices into the four by four complex matrices in some unital way? And well, we can do it as follows. We can take our 2 by 2 matrix and send it over to the 4 by 4 matrix that just has two copies of this matrix along the diagonal. One important property of this embedding is that this embedding preserves the normalized trace. By normalized, I mean you take the normal matrix trace and you divide by the size of your matrix. So in this case, the trace of the left-hand side will be A11 plus A22, all divided by 2. And on the right-hand side, well, you have two copies of A1, two copies of A22, but you're now dividing by 4, so the trace is the same. Well, why stop there? We can do the same thing with putting M4 inside the 8 by 8 matrices in a unital way by doing the exact same thing. We take the 4 by 4 matrix on the left and we place it along the diagonal twice. Once again, the embedding preserves the normalized trace on the matrices. So we can continue this process forever, and we get trace preserving unital embeddings of m2 to the n inside m2 to the n plus 1, just as before, by placing it along the diagonal twice. Um, oops, sorry. So we can view m2 to the j as a subalgebra of m2 to the n for any j less than n, where m2 to the j sits inside m2 to the n, well, 2 to the n minus j times along the diagonal. If we take a union of all the matrix algebras, this will contain a copy of each m2 to the n in some trace-preserving way. Then lastly, to get our algebra R, what we do is we take some sort of closure. We embed each m2 to the n inside some b of h, some bounded operators on a Hilbert space, and we take some sort of strong operator topology closure. And this will give us our hyperfinite 2-1 factor R. So one of the key properties that all the matrices have is that they have a unique normalized faithful trace, right? The normalized matrix trace. And this embedding always preserved the trace of the embeddings. This embedding is trace preserving. Um, so it makes sense that our limiting algebra R, just some sort of inductive limit or some sort of union of all these matrix algebras, will also have a trace. What exactly is a trace? Well, it's as follows. So if we have some unital C-star algebra or von Neumann algebra, a faithful trace on A is a linear functional tau such that number one is unital, so it sends 1 to 1, and it's also equal to the operator norm. 2, tau is tracial, so tau of AB equals tau of BA for all A and B in our algebra A. And lastly, it's faithful. So for all x in A, if tau of x star x equals 0, then x equals 0. Each m to the n, as I mentioned, has a unique faithful trace, and the embedding is trace preserving. So it induces a unique faithful trace tau on R. Showing that this thing is actually unique is a little bit involved, but it can be done. This leads to the definition of what we call a two-one factor. So if M is an infinite dimensional von Neumann algebra with a unique faithful trace, we call M a two-one factor. Now R isn't just any two-one factor. R is what we call a hyperfinite two-one factor. So a two-one factor is hyperfinite if it's some inductive limit of finite dimensional algebras, just like R was. I'm being a little bit vague, but yeah. So I'd be remiss, even though the talk's not about two-one factors or amenable von Neumann algebras and all this, I'd be remiss if I didn't at least mention Kahn's theorem, which is maybe one of the most, if not the most powerful theorem in all of the theory of von Neumann algebras, amenable von Neumann algebras, and it gives an equivalence of hyperfiniteness with a whole bunch of other different properties. So a von Neumann algebra M, which sits inside B of H, and again, we can embed R inside B of H by embedding each M2 to the N inside and taking a union. So our von Neumann algebra is amenable if there exists a linear map E from B of H onto M such that number one, E preserves positivity. So if we have some positive linear operator, then E of T is also positive or not negative. Secondly, it's unital, and E is what we call an M bimodule map, which means if you have two elements, x and y in M, and some linear operator on B of H, then E of xty is equal to x E of ty. We call such a linear operator E, we call E a conditional expectation onto M. So Kahn's theorem says that for any von Neumann algebra sitting inside B of H, M is amenable if and only if M is hyperfinite. This is a crazy powerful theorem. Showing hyperfiniteness implies amenable isn't that bad, but going the other direction is really surprising because just from this very abstract characterization, you get some sort of finite dimensional structure on M. Okay. A consequence of this, and also due to work of Murray and von Neumann, is that R is the unique, to isomorphism, hyperfinite two-one factor, and due to Kahn's theorem, it's also the unique amenable two-one factor. There's one technical thing I need to mention is that R is the unique separably acting two-one factor, but for our case, all of our Neumann algebras will be separably acting. That is the Hilbert space they're embedded into is separable. Okay. So using this theorem, we get other descriptions of R as well, because all we need to do is find some hyperfinite or amenable two-one factor, and by this theorem, it'll be equal to R. So for our first example, we can do exactly what we did for the construction of R, but just by picking a number other than 2. So if we fix some k, at least 2, just like how we embedded m2 to the n inside m2 to the n plus 1, we can embed mk to the n inside mk to the n plus 1 as well. Then we take a union, we embed these into B of H and take some sort of strong operator topology closure, and this will be isomorphic to R as well. For instance, we can do this with m3 to the n. This will be relevant when we're talking about what the right C-star algebraic analog of R should be. One other construction that I'll bring up is suppose we start with a discrete amenable group, and suppose G has the property that every conjugacy class of G is infinite. One such example is S infinity, the permutations of the natural numbers that fix finitely many, that don't fix finitely many, sorry, have finitely many indices that aren't fixed. We then define the space little L2 of G to be the Hilbert space with an orthonormal basis indexed by these functions delta G, where delta G is just the indicator function of the element G. So delta G of H is 1 if G equals H, and it's 0 otherwise. So this is a Hilbert space where we declare this to be the orthonormal basis. We can then define what's called the left regular representation, lambda, going from G to B of L2G. That sends lambda G acts on our basis element delta H just by shifting the basis element to the basis element of GH instead of just H. Then we can define this von Neumann algebra LG to be you take your group G, you map it over to B of L2G, you take V lambda, and you take a strong operator topology closure. And yeah, you get your algebra LG. Um, since our group started off amenable, and since it has infinite conjugacy class, you can show that this will be an amenable 2n factor. Oh, apologies, this should be uh, mapping the group algebra, so finite linear combinations of G, not just G itself. But yeah, this will be an amenable 2n factor, so by Kahn's theorem, we get another description of R here. Okay. There's one last fairly abstract characterization of R that we're interested in, or that's really interesting, and it's the following. Suppose we have any 2-1 factor, then we can always find a unital, trace preserving, and in fact normal, which means like weaks are continuous, embedding of R into M, and R is the unique 2-1 factor with this property. So R is in some sense the smallest 2-1 factor because it embeds into every 2-1 factor. This brings us to the question. Let's say we're in the land of C-star algebras now. What is a C-star algebraic analog of R? So R has some properties that we would want to hopefully transport over to the C-star algebra world. R is unital. It's amenable. It has a unique faithful trace, and it is in some sense the smallest 2-1 factor. It embeds into every 2-1 factor. So whatever our C-star algebra, our analog is, it should be unital. There's a notion of amenability, or aka nuclearity, for C-star algebras as well. So we want our C-star algebra to satisfy this. It should have a unique faithful trace, and in some sense be the smallest for the class of classifiable algebras. Now, what is a classifiable algebra? Classifiable algebras are those unital C-star algebras with quote unquote nice enough properties. So they're simple, they're separable, infinite dimensional, and they have some regularity properties. And importantly, their properties are nice enough such that they're classified entirely by K-theory and traces. If you don't know what K-theory is, it's a sort of topological invariance. Comes from the theory of vector bundles originally in the commutative case. And again, it just tells you it's just an invariant that you can use to classify algebras. Right. So when it comes to classifiable algebras, will be my analog of 2-1 factors. So what would a good first guess be? So naturally, what we can do is we can just take the construction for R that we did and just try and repeat that in the land of C-star algebras. So we took M2 and put it inside M4, put that inside M8, and so on. We took a union. We took a von Neumann algebra closure. But let's do the same thing, and this time just take a norm closure instead of a von Neumann algebra closure. We get this algebra called M2 infinity, or also the canonical anti-commutation relation algebra, the Carr algebra. And it does have a lot of nice properties. It's unital, it's amenable, it's classifiable, it has a unique faithful trace, but it has a bit too much, in quotes, K-theory to be the smallest. Um, the K-theory, you have a K-theory obstruction on being able to embed into any classifiable algebra. One more reason that we might think this is a wrong guess is that, well, for R, it didn't matter what number we picked here. We could have done the same thing with M3 instead. And if we define this algebra M3 infinity to be this inductive limit of these M3 to the n's, well, unlike R, they're not isomorphic. The reason again being these have too much K-theory. And in fact, we can say more than just that they're not isomorphic. There's a K-theoretic abstraction showing that there can be no embedding of M2 infinity inside of M3 infinity. So M2 infinity is not the smallest. Um, the answer, though, is the Jiangsu algebra. This is heuristically just some sort of average of all of the Mn infinities, thus solving the problem that we had on the previous page. So how do we define it? Well, it's built out of these rather scary looking building blocks, but they're not too complicated once you break it down. So given P and Q coprime, we define this algebra ZPQ to be the set of all continuous functions from the unit interval into this algebra MP tensor MQ with two boundary conditions. Number one, on the left-hand side, at 0, we require that f at 0 lands in the left-hand side, MP times some scalar. And on the right-hand side, we require that it lands in MQ. So in some sense, this is an average. This ZPQ is some sort of average of MP and MQ, right? So if P and Q were 2 and 3, this would be some average of like M2 and M3 somehow. Then the Jiangsu algebra is defined as a suitable inductive limit or some sort of closed union where as Pn and Qn go off to infinity, where we embed Zpn Qn into Zpn plus 1 Qn plus 1 in a very clever way. Again, this resolves the issue that these aren't isomorphic because we're just averaging over all of the coprime numbers. So this theorem right here tells us all of the nice properties of Z, or a lot of them. The Jiangsu algebra is a unital, infinite dimensional, classifiable, in particular amenable, algebra with a unique faithful trace. And we have the analog of the property for R that we had, which is that given any classifiable algebra A, we can find a unital embedding of Z into A. One very interesting comparison is with the complex numbers themselves. So Z has the same invariant, so same K-theory and traces as the complex numbers, but it's infinite dimensional. So we can view Z as an infinite dimensional analog of the complex numbers. One more reason this comparison is pretty cool is that, well, C embeds inside any unital C-star algebra, and Z embeds inside any classifiable algebra. So C is in some sense the smallest unital algebra, and Z is in some sense the smallest classifiable algebra. One thing that I would be remiss to not talk about if I'm talking about Z is the classification theorem, which says the following. Suppose we have two classifiable algebras, then A and B are isomorphic if and only if their Elliott invariants, aka K3, K-theory, and traces, are isomorphic. How does Z play a role here? Well, the Jiangsu algebra is the unique classifiable algebra, which does nothing on the invariant when you tensor with it. So I give you a classifiable algebra A. Well, the invariant of that will be the same as the invariant of A tensor Z. So you might be thinking, well, the classification theorem says that you classify by the invariant, and well, we have an algebra A and an algebra A tensor Z that have the same invariant, so logically they must be isomorphic, or this might not be classifiable, but that is. Um, and consequently, one of the key properties or one of the key conditions for an algebra to be called classifiable um, is that A is isomorphic to A tensor Z. This is when I say regularity properties, this is one of the key properties I mean. What this condition gives you, this A being isomorphic to A tensor Z, is some regularity properties on the positive elements of A that allow you to get some notion of comparison similar to comparison of projections in von Neumann algebras. One last comparison I want to make between Z and the hyperfinite 2-1 factor is that Z itself is isomorphic to Z tensor Z. And if you look in the von Neumann algebra side, R is indeed isomorphic to R tensor R as well. There's one last algebra that I want to mention that's a pretty cool non-unital analog of Z. It's called the Razak-Jacelin algebra, which we denote W. Briefly, this is a theorem due to Razak and Jacelin for the first part, and the second part on this embeddings is going to appear in paper due to many people, but it's going to be classification two, the second part of this classification program. So W has an infinite dimensional, or is an infinite dimensional, non-unital classifiable algebra with a unique faithful trace and trivial K-theory. So by non-unital classifiable algebra, I'm being a bit vague. Um, just think of them as the non-unital analogs of classifiable algebras. Importantly, given any non-unital classifiable algebra A, we can always find an embedding of W into A. So, in some sense, W is the infinite dimensional analog of the zero algebra. It's the smallest non-unital classifiable algebra. Just how the zero algebra embeds into anything, W embeds into any non-unital classifiable algebra. Um, but there's also a sense, which I'm not going to delve in too much, in the way that W is maximal in some sense. If you know what the Kunze algebra O2 is, this is a some finite analog of O2 as well. So we're going to take a little bit of a detour to talk about ultra powers now. Ultra powers are a construction which lets us take properties of our algebra which are approximately true and turn them into properties which are on the nose true. Um, so the definition is as follows. Suppose we have a C star algebra A, and suppose we have some free ultrafilter, call it omega on N. If you don't know what a free ultrafilter is or what an ultra limit is, anytime you see the limit as n goes to omega, just think limit as n goes to infinity, maybe along a subsequence. All an ultra filter lets you do is pick out a convergent subsequence. So what we do is we define this ideal I omega to be the set of all bounded sequences in A. So this is the space of all bounded sequences in A, norm bounded, such that the limit as n goes to omega of the norm of an equals 0. Again, it means that we can choose some subsequence going to 0 in some uniform way. As you can show, this thing is in fact an ideal. So what we can do is we define the ultra power of A to be L infinity of A, modded out by this quotient. This is a C-star algebra. Its norm is given by taking some representative sequence for your equivalence class and taking the limit as n goes to omega of the norm of the representative sequence. You can show this is well defined. This makes it a C-star algebra and all that. We can do something very similar for 2-1 factors as well. So if m is a 2-1 factor with unique faithful trace tau, first of all, we get what's called the 2 norm on M, which is a different norm than the norm, the usual like operator norm. It's defined by the 2 norm of x is tau of x star x, take a square root. And what we can do is we define this ideal I upper omega to be the set of all norm-bounded, operator norm-bounded sequences such that xn converges in 2 norm to 0 along our ultrafilter. Then define the tracial ultra power of M to be L infinity of M mod this ideal. And this will be a 2-1 factor. And for instance, a trace will be given by the trace of some sequence will be the limit as n goes to omega of the trace of, well, that sequence. Okay. So our ultra powers naturally contain the algebra itself inside. Via the constant sequences. Um, Formally, what I mean is that there's a natural diagonal embedding delta A going from A into the norm ultra power that sends our element A in A to the equivalence class of the sequence A forever. And yeah, from now on, we'll always view A as sitting inside as ultra power just via the constant sequences. As you can imagine, we can do a very similar thing for 2-1 factors where we just replace the norm ultra power by the tracial ultra power. As I said before, ultra powers let us transport approximate properties into properties that hold just on the nose. Let's see some examples. So first, suppose we have some C-star algebra and some bounded sequence AN of elements which satisfies that AN and B commute in the limit for all B and A. So the limit as n goes to infinity of AN times B minus B times AN is equal to 0 in norm. And what the ultra power lets us do is find one single element that commutes on the nodes with all elements of A. So what is that element? We just take the equivalence class of our sequence. So we set little a to be the equivalence class of the sequence an, and then you can check that A satisfies AB minus BA equals 0 for all B and A. One more example that's very similar or that's very useful in classification type results is that if we have two C-star algebras A and B, and if we have some sequence of maps, phi n, from B to a sequence of linear contractive maps, such that in the limit, phi n looks like a star homomorphism. So formally, phi n of b1, b2 minus phi n of b1, phi n of b2 equals 0 in norm, and the limit as n goes to infinity of phi n of b1 star minus phi n of b1 star is equal to 0. Then we can define a honest to God star homomorphism from B into the norm ultra power given by B gets sent to the sequence phi n of B. Take the equivalence class. Okay. So turning our attention to Z and R in particular, this diagonal embedding is really cool. For R, and we'll have an analogous result for Z, a theorem of Young's tell us that up to unitary equivalence, which is just some notion of natural notion of equivalence of homomorphisms, that the diagonal embedding is the unique trace-preserving unital normal embedding of R into its tracial ultra power. Now, what this lets us do is the following. So suppose we have some embedding of R into some 2-1 factor, trace-preserving, unital, star homomorphism, all that. Suppose we can find any embedding, psi, of M into the tracial ultra power of R. Well, when we compose them, we get a map from R into R omega, which by Young's theorem, this is the diagonal embedding, again, up to equivalence. What this does is motivates the following definition, which is really important in model theory, that of an existential embedding. So suppose we have an embedding phi of 2-1 factors. We call phi existential if there exists an embedding psi from n into the tracial ultra power of m, such that the following diagram commutes. We go from m to n via our embedding, n to omega via the embedding that exists, and this should commute with the diagonal embedding. Again, we can make a similar definition for classifiable algebras where we replace this with lower script omega as well. So roughly speaking, from a model theory perspective, an embedding is existential if for every approximately solvable system of star inequalities, star polynomial inequalities, which have coefficients in M, if that has a solution in N, then it must already have some approximate solution in M. So it lets us lift solutions in N to approximate solutions in M. Um, one more definition that we'll need, one very natural one, is that if M is a 2-1 factor, we call M existentially closed for the class of separable 2-1 factors if every embedding of M into a separable 2-1 factor is existential. Now, whenever we have a property of 2-1 factors, we should ask, does R satisfy this or not, right? It's probably the simplest case to ask. In this case, it is known that R is not existentially closed. And the proof is really cool and really short. So um, suppose we know the following facts. R embeds into any separable 2-1 factor. If we had an embedding of R into M, this embedding is existential if and only if we can find an embedding of M into R omega. Why is this? Well, it's because the diagonal embedding is unique up to unitary equivalence. Thus, we see that R is existentially closed if and only if every separable 2-1 factor embeds into the tracial ultra power of R. Guess what? That's exactly the Kahn's embedding theorem, the Kahn embedding theorem. And famously, the Kahn embedding theorem was disproved in the quantum information paper MIP star equals RE, Thus, we conclude that R is not existentially closed. This brings us to the very last thing I want to talk about, which is Z existentially closed? Um, or what are the existential embeddings of Z, really? We have this theorem of Farah, Hart, Rotem, and Takwesis, which is the analog of the uniqueness of the diagonal embedding for R, which says that the diagonal embedding of Z into its uh, norm ultra power, again, is the unique unital embedding up to unitary equivalence. So just like in the two factors case, to determine if an embedding of Z into its or Z into some classifiable algebra is existential, it reduces defining an embedding of our algebra A into the norm ultra power. So, question which I'll let Ben elaborate on is for what unital C-star algebras A does there exist an embedding of A into the ultra power of Z? Thank you.
Austin, for this ultra nice talk. Do we have some questions? Okay, people are apparently they have understood everything. So it seems, I mean, is there someone from the online audience that has a question? Okay, there's one question from Karen. So 1 second.
Can one also look at such things for other strongly self-absorbing C-star algebras?
Yeah, I believe the theorem of Farah, Rotem, and Takwesis is that if you have any strongly self-absorbing algebra, the diagonal embedding is unique. So again, it reduces to the question of finding embeddings of your algebra into the ultra power. For that, I mean, you have this result which tells you exactly which algebras are strongly self-absorbing, at least I think UCT algebras, like classifiable algebras, and it's like the O2, O infinity, the UHF algebras, and stuff like that. So it's like a fairly concrete list which you can check, but I don't know if there's any general theory about it.
Okay, thank you.
Okay, since there are no questions, let's thank Austin for the nice talk. And now there's a short break, and then we have the main seminar.